Hi, welcome everyone. In this Python notebook, we are going to solve case 1 of this project. That is, we solve the truss with loading obtained from fabrication error and no live loads using regular truss elements. This is the problem that we are going to solve. This is taken from Structural Analysis 8th edition by R.C. Hibbeler. This truss has 3 members, of which member 1 and 2 is 5 mm short. This shortness will make the truss to deform in some unusual ways. Our objective is to evaluate the support reactions and vertical displacements at node 3. When this problem is solved using virtual load method, an upward displacement of 3.33 mm is observed. Our objective is to see whether we are getting the same using OpenSeesPy or not. Validation against a known solution is very fundamental to finite element analysis. This project will teach you how to do a validation. Let's start this case. The first step is to verify whether the Python libraries we need are installed or not. If installed, that's fine. If not, you can install them using pip or conda. For verification and installation, you can use pip show and pip install commands. Our project needs following libraries: OpenSeesPy, OPSWiz, Matplotlib, NumPy for various purposes, such as OpenSeesPy is used for finite element analysis, OPSWiz is used for visualization of the finite element model, Matplotlib is used for creating custom plots that are not supported by OPSWiz. NumPy is a generic linear algebra library which we use for um, matrix and vector operations. Let's import them into our current notebook. I imported them as using these names: OpenSeesPy as OS, OPSWiz as OSV, Matplotlib as PLT, NumPy as NP. You can use your own names. After importing, the next step is to gather all the geometric and material properties. Here we define three arrays: n1 coords, n2 coords, n3 coords. In these arrays, I stored the nodal coordinates of the truss members. All three members has same cross-sectional area, that is 400 mm square. All three truss members have same Young's modulus, that is 2 e power 5. After defining the geometric and material properties, let's create the finite element model. First, we will issue the OpenSys wipe command. This command deletes all the OpenSeesPy objects that were there in the workspace. When running our first simulation, this does not have any effect because there are no OpenSeesPy objects created before. However, when running the model for the second time, it matters because some of the OpenSys objects from the first simulation exists. We need to delete them before starting our second simulation. If you do not delete them, the previous objects will get interact with the current objects and we get some errors or some garbage results. That's why deleting them is very important. That's why we are issuing this OpenSys.wipe command. Then we issue the model command. This command sets some basic parameters such as the dimension, whether it is a 2D or a 3D model, and if it is a 2D model, how many DOFs exist per node, such kind of data. Our model is a 2D model. That's why we put NDM is equals to 2 and NDF is equals to 2. NDF refers to the number of degree of freedoms per node. NDM refers to the number of dimension of the model. Ours is a 2D model, hence it is 2. Next, we create nodes using node command. Our model is a 2D model, hence defining x and y coordinates are enough. Since I have already created this nodal coordinates upfront, so I am just using them from the previously created arrays. Next, we create the elastic material object using uniaxial material command. Here we give the Young's modulus as an input argument. Since it is an elastic material, only Young's modulus is enough. Later, we create the truss elements using element object. Here we give the inputs such as node number, cross-sectional area, and the element number as inputs to this element object. This model has two supports, one hinge support and the other one is a roller support. That's why we are applying the two constraints at nodes 1 and 2 using this fix command. As given in the problem, the truss member connecting the nodes 1 and 2 is 5 mm short. We apply this 5 mm short as a displacement load at node 2. In OpenSys, we define any load as a series of steps in time. We divide the entire load into certain finite number of steps and apply them one by one. Here, H load is defined as 1. because in displacement control analysis, the amount of horizontal load we apply serves as a factor. In simple terms, in displacement control analysis, we apply displacement and OpenSees evaluates corresponding load required to get the displacement and gives that load as output. While giving this output, this load is factored based on the given horizontal load. Means if evaluated load is P and H load is 2, then the output is P by 2. If H load is 1, then output is simply P. No factoring is applied. For load application purposes, we have created a time series, pattern and load objects. Using these three objects, we apply the load onto the structure. This is the model that we have developed so far. So we have three truss members connected in this fashion, and a hinge support is applied at node number 1 and a roller support is applied at node number 2. We obtained this kind of visualization using plot loads 2D command, which is available in the OpenSys visualization library. Our next step is to give the analysis settings. Here each command has a specific purpose. I have written what each command does very specifically here actually. So please go through these comments to get a brief understanding about what each command does. In short, for example, this OpenSys wipe analysis, this command deletes any analysis settings that we have defined before. Constraints applies boundary conditions to the model. Number object specifies numbers to the each DOF. Algorithm specifies the way to update tangent stiffness matrix. In linear analysis, we won't update any stiffness matrix, but this stiffness update is very essential in nonlinear analysis. Integrator sets Ax equals to B equation and rearranges matrix components depending upon the analysis types. It is a simple linear analysis, hence we apply the entire load in one step. Then we issue the analyze command, and this analyze command performs the analysis for all the number of steps, and the analysis status will be stored in this pushover analysis status variable. If the analysis is successful, then this os.analyze command returns 0 value. If the analysis is not successful, means it failed at any intermediate step, then it returns some value other than zeros. So that's why we put a if condition to verify whether this pushover analysis status variable has a value 0 or not. So if it is 0, then we are treating it as analysis successful. If it is not 0, then we treat it as analysis failed. Let's see what we have got from the analysis. So here we do the post processing. Post processing means we will see what kind of displacements we have got, what are the nodal reactions that we have got, and the member forces that we have got, and how are they with respect to our analytical values. Let's see how we have got. Using os.nodeDisp command, we can evaluate the displacement at a particular node. This command requires two input, that is the node number and the DOF. One refers to horizontal, two refers to vertical. That's what we are asking OpenSys. We are printing those displacements. So if you look at the X displacement is minus 2.5 and the Y displacement is 3.33333 and so on. So positive sign in UI3 represents the upward direction, and the analytical solution that we have got from unit load method is 3.333 mm upward direction. Hence our OpenSys model is perfectly predicting the analytical results. It means our model is accurate. Let's see how the model deforms. The dotted line in this image shows the original undeformed model, whereas the blue line in this image shows the deformed model. If you look at here, the blue line shifted its position slightly upwards. It means the deformation is going in the upward direction due to the 5 mm fabrication error. Like the nodeDisp command, we can get the nodal reaction also, but one caveat here is if you want to get the node reaction, we have to apply this os.reactions function. We have to activate this function first. After giving this command, OpenSys will evaluate the reactions and keep it ready for node reaction command. So first we have to give this os.reactions, then we have to issue this node reaction. Node reaction also takes two inputs. First one is the node number, second one is the DOF. One refers to the X direction, two refers to the Y direction. When we record the reactions at nodes 1 and 2, what we have got is the Rx1 value is 50,000 and ry1 is 0 and rx2 values are 0 and ry2 is 0. Similarly, when we evaluate the element response, the member forces that we have got is in members 1 and 2, we have got some 50,000 compressive force, and in members 1, 3 and 2, 3, we have noticed the 0 and 0 newtons internal force. When we look at the member forces that we have got from virtual load method and reactions from regular equilibrium equations, what we have got is we noticed an X reaction of 50 kilonewton, the same that we have got from the OpenSees model, and the member forces of 50 kilonewton compression force in members 1 and 2, the same thing that we have noticed in OpenSees results as well, and we noticed some 0 results in members 1, 3 and 2, 3. That's it. Our OpenSees finite elements have correctly exactly evaluated the results of this truss. If you have any questions or need any help, you are always welcome to post them in the course discussion forum, and also you can always email them to elastropy@gmail.com. Happy learning. Thank you.